We've previously gone over the first two sections of Chapter 7, which are centripetal acceleration and Newton's law of universal gravitation. Now we're moving on to look at motion in space. Some critical methods for describing motion in space come from Keplers Laws. This is a series of 3 laws of planetary motion created by Kepler, who was an astronomer in the 16th and 17th centuries. So the first of Kepler's laws states that each planet travels in an elliptical orbit around the Sun, and the Sun is at one of the focal points. So you might know from math class where the focal points of the ellipse are. I haven't drawn these exactly to scale, but that's roughly the location. So this law states that the Sun will be at one of these focal points, and the planet will rotate in an elliptical or sort of oval-shaped pattern around the Sun. Keplers' second law states that an imaginary line drawn from the Sun to any planet sweeps out equal areas in equal time intervals. So if you sort of visualize this, you can see that even though a planet is moving in an ellipse, the area over here on this side that I'm coloring in blue will equal the area I'm coloring in black on this side. That's because as the object moves closer to the Sun, it will speed up in its orbit, making these two areas the same over equal time intervals. Finally, Kepler's third law, and perhaps the most important for our calculations, states that the square of a planet's orbital period, or t squared, is proportional to the cube of the average distance, or r cubed, between the planet and the Sun. So we write this as t squared is proportional to r cubed, as you can see right here. And this law, amazingly, is consistent with Newton's law of universal gravitation. So the two scientists kind of worked off of one another to develop these two laws about the planets. Let's take a look at some applications of Kepler's third law. So we have this equation written at the top that we've just learned, t squared is proportional to r cubed. And it's accepted that the constant of proportionality for this equation is equal to 4 pi squared divided by g times m. So we can rewrite this plugging in this expression to get that t squared equals 4 pi squared divided by gm times r cubed. So from this, we can simplify by taking the square root to get that the period t of an object in orbit is equal to 2 pi times the square root of r cubed divided by g times m. So this is the mass of the object, and this is its radius from the body that it's orbiting. And then we also have this equation for the velocity of an object in orbit, which is that v, or velocity, equals the square root of g times m over r. We're going to be using these a lot in future calculations. Here's some practice with Kepler's laws. Number 1. A satellite orbits Earth with a mean altitude of 361 kilometers. If the orbit is circular, what are the satellite's period and speed? So first let's look at some of the facts we already know about the satellite. We have its altitude, which is 361 kilometers, or 361,000 meters. And we're looking for its period and its speed. Now we also, to find its true altitude, or the distance that we'll plug into this equation, we're going to need to add the radius of the Earth. So we know that the radius of the Earth is about 6.38 times 10 to the 6th meters. And then if we add on these 361,000 meters that the satellite has an altitude above the Earth, we get that the radius is 6.7 times 10 to the 6th meters. We also will need the mass of the Earth, which we know is approximately 5.97 times 10 to the 24th kilograms. Now we're ready to solve. So we learned on the previous slide that the equation for the period of an object that's orbiting a planet is 2 pi root r cubed divided by g times m. If we plug in all the numbers that we have, we get that this is 2 pi root. The radius we found is 6.7 times 10 to the 6th. We're going to be cubing that, and then we'll divide by 6.67 times 10 to the negative 11th times the mass of the Earth, which is 5.97 times 10 to the 24th. That's a pretty complicated equation with a lot of scientific notation, but we're going to multiply all of that out. We'll get that t is equal to 2 pi times about 877. So the period of the satellite is going to be 5,510 seconds. Now we're solving for the velocity. I'm actually going to go to a new slide here so that we can have more space to solve. So again, we're on problem 1 of practice in section 3 of chapter 7, and we're solving now for the velocity of a satellite that's orbiting the Earth. So we know the mass of the Earth. I'm just going to briefly jot these down so that we have them to look at. So this is 5.97 times 10 to the 24th kilograms. Then we have the radius of the satellite, which we solved for by adding the altitude of the satellite to the radius of the Earth. So that's 6.7 times 10 to the 6th meters. And then we also know that the equation for the velocity of an object orbiting a planet in space is going to equal the square root of g times m over r. Now we know all of these values that we're going to need except for velocity, which is what we're solving for. So we'll plug it in. We get that v is the square root of g, so that's 6.67 times 10 to the negative 11th, times the mass of the Earth, which is 5.97 times 10 to the 24th, divided by the radius, which is 6.7 times 10 to the 6th. Then we're going to plug in all of those numbers, and we'll get that the velocity of the satellite is about 7,700 meters per second. Number 2. The same satellite from problem 1 now orbits Jupiter at the same altitude as before, which is 361, and I'm sorry, this should say kilometers. What are its new period and speed? So let's look at some known facts about Jupiter. We know that Jupiter's mass, or m sub j, is about equal to 1.9 times 10 to the 27th kilograms. We also have the radius of Jupiter, or r sub j, which is 7.25 times 10 to the 7th meters. And we know that the radius of the satellite will be its altitude, so 361,000 meters, plus the radius of Jupiter, which is 7.25 times 10 to the 7th meters. And then if we add those two together, we get that its overall radius is about 7.3 times 10 to the 7th meters. Now it's time to plug these numbers into our two equations. So first we have the equation for period, which will be equal to 2 pi times the square root of r cubed divided by gm. Now we'll plug in all the numbers we know. We have r, which is 7.3 times 10 to the 7th. We're going to cube that. And then on the bottom we have g, which is 6.67 times 10 to the negative 11th. And we have m, which is the mass of Jupiter, so 1.9 times 10 to the 27th kilograms. And then we'll multiply all of that out using a calculator, and we get that the period of the satellite when it's orbiting around Jupiter is 11,000 seconds. Second, we're going to be solving for the speed once again. So we have this velocity equation, v equals square root of g times m over r. We'll plug in our known values. 6.67. Mass is 1.9 times 10 to the 27th. And then finally we have radius on the bottom, which is 7.3 times 10 to the 7th. Again, we're going to do some multiplication with the calculator to find that the velocity of this satellite will be 41,600 meters per second.